All right, guys, what I'd like to do today is just take these two equations that are in rectangular form and work through the manipulation to get them into polar form, okay? Now, obviously, if I wanted to graph this, we know, going back to Algebra 1, like if I choose my x values, which are my independent variable, right, they're going to spit back y values when I plug in evaluate. If we do that, we can graph it. We only need 2 points, that kind of thing. So great, we can do that. Is that okay with everybody? Now, we want to put in polar coordinates, okay? So in order to do that, we need to have a replacement for x in polar form. We need a replacement for y in polar form. Do we remember what those are? Okay, so if x is equal to r cosine theta, right? And y was equal to r sine of theta, okay? Now, we're also going to need eventually this relationship that r is equal to x squared plus y squared underneath the square root, okay? Now, that's not the version that we're really going to need, and we're not going to need it in this equation, but some will. What we will really need is if I take this thing and I square both sides, it gives me x squared plus y squared, right? And the reason we'll need that is look over here. Can you visualize that there's going to be an x squared plus y squared over there? So I'm going to need to be able to replace that somehow. Okay, so we'll do that with r squared. All right, so now with this, so this is in rectangular form, which means, obviously if I plug in x to be 0, I would get y to be -6. If I plug x to be 1, I would get y to be -3, right? Okay, and we could graph that. Wouldn't be a big deal. Okay, if we convert it into polar, we would be now saying that 3, but instead of x, we're going to replace it with r cosine theta. And instead of y, it's r sine theta is equal to 6. Okay. Now it's a fully functional polar equation. What we're going to find out, some of our graphing tools, especially like Desmos is an implicit grapher, so we can leave it that way, type it in just like that, and it'll graph what we need. Okay. But I want to transition to something that's a little bit more explicit. Okay. So what do you see that both of these terms on the left-hand side have in common? They have r in them. So I'm going to say r, I'll factor that out, and I get left with 3 cosine theta minus sine theta is equal to 6, right? Can I solve that for r? So through division, I can find that r is equal to 6 divided by 3 cosine theta minus sine theta. Okay. Now when I make a table to graph this, okay, and I'm going to say r comma theta, but it's a little bit different in how we evaluate, okay? Previously, we would choose x to evaluate, x being the independent variable, right? Theta is the independent variable here in polar, okay? So let's choose a value of theta. Give me a value of theta that makes maybe sense for evaluating cosine and sine. I think, anybody say 0? Nobody said 0? Maybe I'm hearing voices. All right. 0 is a good, if I'm just going to evaluate sine and cosine, and I have no limitation, I have no structure here, nobody's telling me you have to say with these radian measurements or these degrees. I like 0 because doesn't that give me outputs of 1, 0, or -1 when I evaluate sine and cosine at 0? So when I plug this in, I'm going to get, so when I plug 0 in, I get 6 times 3 cosine of 0 minus sine of 0. Well, what is cosine of 0? It's 1, right? So it gives me 3 here. What's sine of 0? 0. That's why I like choosing 0, because it gives me now 6 divided by 3. That's easy work there, right? Okay. So 6 divided by 3 is 2. Okay. So we get the ordered pair in polar form of r being 2 and theta being 0. Now, I heard somebody say pi over 4, which is fine. It will work. But what is cosine of pi over 4? Yeah, radical 2 over 2. And then what is the sine of pi over 4? Radical 2 over 2. So I'd have 3 radical 2 over 2 minus radical 2 over 2, right? So then I'll have 2 radical 2 over 2, I believe, which will give me just radical 2, correct? Then I have 6 divided by radical 2. Can you in your head do 6 divided by radical 2? Okay, you get 6 radical 2 over 2, you get 3 radical 2, right? But can you graph that? Do you know where 3 radical 2 is on a graph? So what I'm trying to get at there is if I can avoid the irrational numbers as outputs for this final evaluation, I'm going to. That's why I don't like to use things like pi over 4. But maybe pi over 2. If I try pi over 2, what's cosine of pi over 2? 0. What's sine of pi over 2? 1. So you get 6 over 0 minus 1 gives me negative 6. Okay. I can try pi. So if I try pi, what's the cosine of pi? Negative 1, right? So I get 3 times negative 1 minus then the sine of pi is 0. What's 6 divided by negative 3? Negative 2. Okay? And I can keep doing that. As many values of theta that I'm interested in. Okay? And what we're going to find out in a couple days is that there will be interest in maybe going from 0 to 2 pi. And sometimes maybe going from 0 to 4 pi, depending on what we have in front of us as the equation. Okay? But if I were to, let's just kind of go back to, I'll use GeoGebra here, and we'll put this one on the right in polar. Okay. So this one over here on the left, so, we said 0, negative 6 was a rectangular coordinate for this line. And we also had 1, negative 3. Okay. So we'll use those 2 points to come up with the equation 3x, or the graph of the equation 3x minus y equals 6, right? That's what we've done that forever, since like 8th grade math, some of us. Okay, maybe even sooner. Now what we're doing is saying over here in the blue graph, well, what if my r value was 2? So let me move this one over here. There we go. My r value is 2. My radius is 2. And my theta is 0. If I plot that point, per how we know how to plot polar coordinates, we get that. Okay. Now, if my r value is negative 6, and my theta is pi over 2, okay, got to put the semicolon, pi over 2, graph that. Okay, now I'll have to zoom out to get to the 6th circle. There it is. Okay. And remember, so it was negative 6 pi over 2. So what we would go is we go over to pi over 2, go up to 6, and because it's a negative 6, then we flop down here, right? Go to the opposite ray. And if I try negative 2, semicolon pi, it gives me back to the same point that E or C was on. But regardless, now if I go ahead and type in Now, I might be wrong here. I'm not sure with the notation and GeoGebra. I might have to go to Desmos to show you this. If I go R equals 6 divided by 3 cosine of theta minus sine of theta There we go. Do those lines look like the same line? Okay. And now the nice thing that I can do in GeoGebra is I can click on this blue graph, go to graphics, change the grid back to rectangular, and you see at this point here was -6, 0, or sorry, 0, -6 like we had over here. This point here is 2, 0, which we can see that would be 2, 0 there as well, right? So we've got a method for constructing a rectangular equation now as a polar equation. Yes. It's just the notation that GeoGebra uses to determine that it knows that the user is using polar coordinates. Because if I put a comma, it's going to graph it like an X and a Y. So that brings us to this next question. So that and my argument is like, and I could be completely wrong in regards to applications of this stuff, but my thought is, okay, if I want to graph 3x minus y equals 6, probably the easiest thing to do is to graph that in rectangular. I think the creation of the polar equation, and that polar equation looks a lot more complex and messy and murky than what it did in rectangular, right? So I don't know that we get a huge benefit from being able to do that with linear equations, but it is something that's possible to do. I think we gain a little bit with being able to do it here, because let's say that I ask you to construct a table of values for x's and y's, okay? And you just randomly start choosing x values and plug them in there. Don't you have to do a lot of algebra then to solve for the y? Does that make sense? This is what we call an implicit equation, and it's pretty nasty. And if I wanted to actually take this implicit equation and solve it for x, then that's going to actually turn into two equations. It'll be the top semicircle and the bottom semicircle, and it's going to incorporate a square root. The plus or minus aspect gives it the top. The plus gives me the top. Do you guys ever do this in Algebra 1? If I solve this for x, that's actually going to, when I graph this, it would give me, like the positive version would give me like that part of the circle, and the negative square root would give me that part. So you probably never really solved it for x. You probably solved it for y, and what you ended up doing is that you would have something like 1 minus x squared that's equal to y plus 1 squared. So you take the square root of both sides. That's where we get plus or minus. And then you subtract 1 from, so you get y equals -1 plus or minus 1 minus x squared. So the -1 plus this stuff would give me like that semicircle, and then the -1 minus this stuff would give me that semicircle. Does that make sense? Okay. But doing it that way, using rectangular coordinates and doing it that way, creates a very complex scenario. Now we've got two equations that need to be used in tandem to create one picture, one image. Okay. And the reason for that is because the circle is not a function, right? Okay. So we need two rules that one will produce kind of that first point that a vertical line would pass through, and then the second point that vertical line would pass through. Okay. Well, if we do this in polar coordinates, we don't have that issue. Okay. Now, in order to get to that, what we need to do is do some algebra here first. I'm going to expand the y plus 1 squared. We'll combine like terms. Okay? Move everything to one side, that kind of thing. So what I'm saying here is that these ones are going to go away, right? So I'm left with x squared plus y squared plus 2y equals 0. What did we say that x squared plus y squared could be rewritten as? R squared. And y can be rewritten as r sine theta, right? So we get 2r sine theta. All right, now what do these both have in common? An r. So this is something that we maybe wouldn't have done in rectangular form, okay? Because you guys remember, like if I divide by a factor, what I end up doing is eliminating a 0. Okay, I lose a 0 by doing that. We really don't have that issue here with this, so I like this factor technique because maybe it avoids having to have that discussion. But if I go, but we got two things being multiplied together to give me 0, right? So doesn't r have to equal 0? And r plus 2 sine theta also equals 0. I'm just going to solve that for r at the same time. So I get those two values for r. Now think about this. What does r represent? Okay, it's the square root of x squared plus y squared, so it is the length of a hypotenuse of a right triangle, or the radius of the accompanying circle, right? Right there, we're saying that your radius is 0, right? So what this does, because that's 0, it really doesn't give us anything. Okay, maybe it gives us a point, if you want to think about it that way. The point 0, 0, but or maybe it's the pole. But we're not going to deal with that. This here is what we're left over with. That's the thing that's kind of almost non-trivial here. Okay? That is the equation of the circle that was up here. Okay? Think about this. This circle here, circle radius of 1. It's centered at 0, -1. Okay? This circle does the same thing. Now, if I look at this, just kind of thinking about, well, why is this easier to compute? Like if I choose a theta value, let's choose theta to be 0. If theta was 0, okay, what's the sign of 0? Sign of 0 is 0, isn't it? Multiply by -2, you get 0. Let's go. I'm going to try to pick off some values that make it easy to multiply. Let's go sine of pi over 6. What's the sine of pi over 6? 1/2, right? What's 1/2 times -2? -1. Let's go pi over 2. What's the sine of pi over 2? 1. What do I get when I multiply it by -2? -2. Let's go to 5 pi over 6. 5 pi over 6 is 1/2, right? Multiplied by -2 is -1. Let's go 7 pi, or let's go pi. Pi is 0, right? Let's go 7 pi over 6. Be -1/2 now, right? So it'd be +1. Is that going to be the same thing for when I get to 11 pi over 6? And then 3 pi over 2 would be, what, +2? So that's just a list of ordered pairs, r, theta, that we know from evaluating off the unit circle, right? Okay. Now, if I were to go through and let's plot those. Try to get it all on the screen here at once. All right, so I'm going to go 0, semicolon 0, negative 1, semicolon pi over 6, negative 2, semicolon pi over 2, negative 1, semicolon 5 pi over 6, 0 pi, 0 pi, we get 1, 7 pi over 6. Okay, so we're seeing some repetition here. 1, 11 pi over 6. And then 2, 3 pi over 2. Should be another one we already have. So we get those, which is fine. I mean, they're a bunch of repeats, though. If we were to find, if we're going to like the pi over 3 and pi over 4 values for theta, we would get more values in between and more points. And what we end up with, if I were to graph this, I'm going to say r equals negative 2 sine, and we'll put theta in there. Does it give me a circle that goes through those points? Okay. Now, if I come over here in the Cartesian plane and type in x squared plus y plus 1 squared equals 1, is it the same circle? Yeah. Okay. But to generate this one, so if I've got like a computer program that is required to take some type of information and move it into some type of code that will then move an object, move maybe a robotic arm in a circle, okay? I would much rather program that with a polar coordinate or polar equation, because then it only has one input, right? If I have to program it with rectangular equations, I have to program it with either the x squared plus y plus 1 squared equals 1, or the explicit version of that for y being solved, which would be then 2 equations, right? It's just a lot messier and a lot more work for the program and the calculations to do it in rectangular than it is to do it in polar. Okay, so it's more efficient. So that's a use for our polar equations. I'll show you maybe on Monday. We'll go through the next